Hello everyone. This will be a mini series where I cover all the stuff that we've covered so far. There will be one video per question, so you can go back and watch it over and over again. So this is meant to be for your final exam, so the main difference here would be that I will try to use less MATLAB help and more theoretical knowledge here, so that it hopefully will help you out for your final exam. So our first question is about the given transfer function, and as usual we try to look for the stability interval for the p-type controller. Now this is a very basic question, but here we will see that there are many methods that you can use in order to determine the stability interval of a p-type controller. And there's also the delay part here, where we can find the time constant of the delay that can be added to the transfer function given here, so that the closed loop remains stable. So let's start. Now, of course, I will still use MATLAB in the background, but just for basic calculations, hopefully, and make a point. So we have a transfer function here, and we are looking for a p-type controller using time domain methods. So one of them is Root Locus, of course, but another one would be to use the transfer function itself and a so-called algebraic method. So let's see. Now, since I know that I have a transfer function and I know that I have a p-type controller, I can define my p-type controller as usual, and I can look for the closed loop transfer function, since that should be remain stable for the interval that I'm going to come up for k. So in this case, what we have to do is we have to directly multiply and divide the following expression, 1 plus k times GSS. So here you have GS, so I can, by the way, immediately see what it should be. Maybe I can go ahead and do it more paper friendly, let's say. So I know that the numerator and denominator is given, and I also know that I have a basic controller, a p-type controller. So let's see the expression in detail. Now this is GSS divided by 1 plus kGSS. So instead of using GSS, let's say NS divided by DS. So the numerator, so let's make it num then. Therefore, so num divided by denominator, and the same for this one. Now, here we have the closed loop transfer function. Most of the time we use num then and then use simplify, but actually this is not really that necessary. What we can do is we can immediately see that from this expression I can derive the following. I can multiply everywhere with the denominator, which would then get rid of this num divided by den, and I would see the following. This would be den plus k times num, and then this is gone. And then here, this is also gone. And then I have a much simpler expression where I can see that k times num divided by den plus k times num is basically the transfer function, closed loop transfer function. What I can also see is that the numerator here is a polynomial. Num would be a polynomial, and den is also a polynomial. So the combination here is also a polynomial, which shows me directly that the PCS would be k times num plus den. So I don't have to really define this here. I can just directly conclude that my closed loop characteristic polynomial would be k times num plus den. In this case, if you're using pen and paper, you can directly conclude that 6k plus the denominator itself will be the closed loop transfer function characteristic polynomial. So once we've done this, we know that the polynomial that we will find here, let's also run it. There we go. Is s cubed plus 7s squared plus 6s plus 6k. Now, of course, if you look closely for this given transfer function especially, it is quite easy to see that k should be positive, because if it's not, then this will vanish and then we will have this times s, which tells us that we have an integrator in the closed loop transfer function for k equals 0, or we have a pole at the origin, which is the equivalent. Therefore, if you look close, you can see directly that k should be positive. But we have to ensure that the stability interval is k greater than 0. So one method would be to look for a j omega axis crossing. And how we can achieve that is the following. We have a polynomial, and we can substitute any type of root into this polynomial, and if it's a root of this polynomial, it should be equal to 0, which means that we have, for example, s equals minus 2 plus 2i. Now, in order to determine if this is the root of this characteristic polynomial, or what k would satisfy this root for this polynomial, or in other words, what k would assign one of the poles to this given pole, would be to plug it in. But in this case, if I'm looking for stability, I'm really interested in the j omega axis itself. So I might go ahead and say, I want to plug in j omega. Now, j omega should satisfy this at some point. And what exactly is that point? So therefore, we could go ahead and plug in j omega. But keep in mind that we have a controller, and this is a closed loop characteristic polynomial, which means that we would have k and omega individually appearing in these expressions, and since we have s cubed, for example, there would be j omega cubed. So now it seems like we have just one equation here and two unknowns, which would be a bit of a problem, but it's really not, because if you look close, or if you remember that j omega is basically a complex number, and plugging in a complex number would give us a real and an imaginary part. And if you're equating to 0, this what it actually means is that you have 0 plus 0i. So this would give us two equations, one of them being the real part of this equation, and the other one would be the imaginary part of this equation. So what we have to do is we have to plug in s equals j omega into this characteristic polynomial, and then take its real part, equate it to 0, take its imaginary part, equate it to 0, and then come up with a solution, hopefully. This should give us k and omega pairs, hopefully. So let's exactly do that. Now we have PCS, so for p omega, for example, let's substitute s equals 1i times omega. So therefore we have to define omega real. Here we go. And then we would have the following. This will be a complex number, and you can see that there is 6 omega I, and then minus omega cubed I, and then there's 6k minus 7 omega squared. So basically, our problem definition would be literally take the real part of p omega, equate it to 0, take the imaginary part of p omega, equate it to 0. So let's see what the equation set here is, basically. There we go. Now we can see that there is an equation, a dedicated equation for omega. So we can come up with omegas here and choose those omega values and plug it in to the other equation, and it will give us the k. So there is a two-step thing to it. We have one to determine omega, the other one to determine k. Now this might be just for p-type controllers, because if you have one more unknown, that will also appear somewhere here, and it will become a bit more harder to see what really the stability interval would be. So for p-type controllers, it's quite easy. So let's solve this problem, but you can immediately see that omega could be 0. That would be one root of this equation, and the other one would be omega squared is equal to 6. Now there could be a positive and negative omega value, but by definition this wouldn't make much sense, so we would take the positive one. So what omega should look like is omega should be 0 and omega should be square root of 6. So square root of 6. And then we can use omega 0, which shows us that k is equal to 0. And we could use omega equals square root of 6, which should give us omega squared equals 6. And then this would be then would correspond to a certain k value, which is even very much easy. So this would be it, and then plus 6k should be equal to 0. Of course, k is then equal to, I guess, 7. Yeah. So let's see what MATLAB comes up with. But you can see that it is numerically not that hard. Let's have the solution. We have 3 solutions. So we have k, and then we have omega. Now you can see that one of the solutions is 0, one of them is squared 6, and the other one is negative squared 6, but we really don't need that one. So now k equals 0 is one of the stability bounds, and the other one is square root of 6. So this system should be stable in the interval square root of, between 7. And for 0, the root would be, this j omega crossing would be through the origin itself. And if you choose 7, it would be square root of 6. Now, this is actually pretty important because if we, for example, look for the root locus, which you should sketch roughly by yourself, this would also be as follows. Now here we can see that this point corresponds to square root of 6 j omega. So this would be square root of 6. Now, if you can click exactly here, there was the square root 6 calculation that I've done. Let's repeat that. 2.44, which is roughly the j omega part here. So it's somewhere here. So we can see that one of the stability bounds is given here, and the other one does not appear on the positive root locus, but it should appear on the negative root locus, since it's a j omega crossing. So we have this one and this one. One of them was the stability bound for the positive root locus. The other one here, you can see that it is immediately at the origin, so the passing occurs where k is equal to 0, where no controller is even present. So now this is basically one way of determining the stability here. Of course, you can go ahead and use the root Hurwitz table. Since you have PCS, you can construct your root table and then look for the stability conditions. It's also possible. So there's also the root locus method itself, where you can determine the stability, where you have to take into account the angle condition here. So since we have the following roots, 1, 7, 6, so we have one root at -1, and the other one is at -6. And then the other one would be at 0. Now for this, you would then go ahead and create the following. Now, let's say we have these roots here, and our j omega, or our destination point here, would be something like this. So since we are at the origin, at this pole, and our destination would be here at j omega, the angle condition that you would write would be 90 degrees, and then the angle from this vector here, and then the angle from this vector should be equal to -180 degrees. So we can directly say that since this distance here is omega, and then we know what the distance here are, we would say that a tan of omega divided by 6, because that is basically the angle that we can write here. So using the tangent here, omega divided by 6 would give us this here. So this plus, and then we have 1 here, and the distance is omega, so a tan omega, and then plus 90 degrees, because the angle contribution at the origin is 90 degrees, should be 180 degrees. So this would be the phase condition or angle condition of root locus. For this angle condition, you should basically have a rough sketch of your root locus plot. Once you've done that, remember that we are looking for the point where j omega is. So yeah, for this angle condition, you can directly see that this sum should be equal to 90 degrees. Now, this is a special case, because in order to have this here, you can directly see that one of the a tan, or the tangent of something, a divided by b, if this is, for example, alpha, if we have alpha here, and if we have tangent of 90 degrees minus alpha, since this would be the case here, what you can do is you can directly get rid of this expression and convert it into the following. So instead of using the following, so we could use the following. Since this, for example, is, let's call it theta, then the tangent of theta would be omega divided by 6. Now, instead of using theta, what we can do is we can say that 90 minus theta, so what is 90 degrees minus theta? This would be the cotangent of theta, and since cotangent of theta would be 6 divided by omega, we can directly see that 6 divided by omega should be equal to omega, because we were looking for this, and we've used basically this here, or yeah, this here basically. So this was theta, 90 minus theta, have the tangent of theta, so tangent of this expression, or in other words, tangent of 90 minus theta. So therefore, we can see that actually that the angle condition given like this would correspond to this equation here. Now, from this equation, of course, we can conclude that 6 equals omega squared, which was already the omega value that we were looking for. So yeah, using that, you have omega equals square root of 6 again, and having that information, you can just use the gain condition, where you look for the distance from this pole to this one, which is omega, and then here we have, which would be omega times square root of omega squared plus 1, because this distance is 1, this distance is omega, so this would be the square root of this, times, again, omega squared plus 6 squared, so 36. So since you would have one value for omega, for example, if you have omega equals 0, this would become 0. If you have omega equals square root of 6, you would have 6 here, and square root of 42 plus 37. Oh, no, 7 actually. So square root of 6, let's do it. Square root of 6 plus 1, which should be 7. And then square root of 42. Yeah, 42. Now, you can see that this will reduce down to square root of 6 times square root of 6, square root of 7 times square root of 7, which makes 42. Now, you would argue that this is not correct because what we found was 7. We found that k was 7 here. Now, how can the gain condition of the root locus method give us 42? Now, what I would say then would be the following. You can see that there's 6k here. So you have to take into account that there's a that the root locus method here gives you the constant term here, and if you have a coefficient in it, in the constant term, then you should take it as a whole. So if you have 6k equals 42, you would say that k is equal to 7. Or in other words, k is equal to 7, and if you plug in k7, you would get 42. So in the characteristic polynomial, you should have 42 in this place. And in terms of the controller, that would be achieved with k equals 7. So this basically gives us the root locus method, and I have shown you basically the algebraic method, which gave us the same result basically. So this is the first part of the question. Let's say k val equals double sol dot k in order to convert this, and then omega val, then omega. So k val and omega val. So here we can see that basically 0 and 7, 0 and 2.4495. So this was part A, where we use the time domain methods. And as I've mentioned, I've briefly mentioned the root locus method. So you can use the root locus phase and gain conditions. Therefore, you need a little sketch. You have to have an idea of how the root locus actually looks. You can use the Ruth table, where you can construct a table of the characteristic polynomial, or you could use the direct substitution method, sort of direct subs method, s equals j omega. So all three methods, and there are many more, will give you the same result here. So let's attack the problem from a different angle, which is the frequency method. So what about the frequency method? Now, for the frequency part, most of the time, you would use the body diagram. So just plug in body GS, and remember that once you have the body diagram, you were looking for a negative 180 degrees, which is this one. You would click on the body graph, it'll take the frequency, go to the gain or magnitude plot, and then click at the same frequency and then read the value that you have here. Convert it, of course, into gain from decibels, and then take the inverse. That would be the methods to achieve or to acquire the information. But what if you are in an exam and you don't have the body plot in front of you? So can't you use the body methods still? So of course you can, and that's also the point that I'm trying to make here. So let's see how we can do that. So body. Now for the body methods, what we should do is we should again plug in s equals j omega. So this looks like the line 20 methods. So the reason why we call it the direct substitution methods, or why we name it in the time domain, is that you're basically plugging in frequency, but you don't use the frequency information here. So this is kind of in the middle between the time and frequency domain. But yeah, now we have GSS, and let's plug in S equals J omega. 1I times omega. Of course, let's define omega real. Even though we have defined it here, let's reset it here. So let's see what it looks like. Now you can see that this is basically J omega. Now, what we need is, we need the following. We need to get the argument of our J omega, and it should be equal to 180 degrees. So if I can calculate this based on this, and then proceed to this other step, to step 2, where we would look for the absolute value of the G omega, but the problem here is to come up with omega star here. What is omega star? So if we have omega star, we would use the same omega star here, omega star, and then we would get the gain, and then inversing it would give us the p-type controller bound. Now, since this is basically a fraction, what I can do is I can see that in order to calculate the argument or the angle of this, what I can do is I can, for example, calculate the angle of this. So GSS here is this minus J omega, I guess. Yeah, okay. Now I could calculate the argument of this. So let me type it out. So instead of calculating the argument of this, if this is a fraction, what I can do is I can get the argument of the numerator, which is minus 6, and then get the argument of the denominator somehow, and then take the difference. So argument of numerator minus argument of denominator. So, and in this case it looks negative, but I can use this negative in here. This should be basically positive. So maybe simplify can help us out, I'm not sure. Yeah, it does not help, but it would also work like this. Let's try that one out. So since this is minus 6, I have the argument of minus 6, and then minus the argument of the given expression here. Let's take it. Minus this argument here. Now, of course, this should be minus 180 degrees, and then minus this expression here. So, since we have this here, maybe, is it possible to get real part? Yeah, but it messes up. So let's get the real part of this, and then the imaginary part, because I would use them to calculate my argument here. So this is basically the same as using A10, and let's get rid of this imaginary part, this part, divided by 7 omega squared. So now since we have minus 180 degrees, and since we are looking for minus 180 degrees again, so what we can see is that this A10 here should be equal to 0, basically. And what is tan 0? It's basically 0. So this equation would give us that this should be equal to 0. Now, since we have omega squared here, and omega squared minus 6 here, and since this is divided by 7 omega squared, what we can do is we can get rid of the denominator here and focus more on the numerator part. But keep in mind that omega equals 0 would not be a solution of this, because we have omega here and omega here. If we cancel them out, we would have divided by 7 omega. So basically this equation reduces down to this one. And omega should not be equal to 0 if we want to satisfy this one here. So keep that in mind. Now this would also vanish, and what we are left is omega squared minus 6 is equal to 0, so omega squared should be equal to 6. Now this is again familiar information, we've already found that, but the way that we've worked this out was to use the transfer function itself, plug it in s equals j omega, and then work our way out in the arguments. So if we use the argument function, we know that a fraction would be the numerator minus denominator arguments, and then we also know that this is a complex number, so having the real imaginary part sorted out and then taking the imaginary divided by real part, a tan, gives us the argument itself. And then we've seen that a negative part was here, so minus 180 degrees. So they cancelled each other out, and then this should have been equal to 0. So working out the necessary steps, we found that omega is square root of 6. So this would be one solution, and if you want to find the other solution, if you remember, we were looking for 0 degrees here. So you have to repeat these steps for omega, for argument equals 0. Now in this case, you would see that a tan should be, I guess, minus 180 degrees, and you using minus pi gives us again 0, then this should be again equal to 0 here. Yeah, but here we can not conclude that omega is equal to 0 exactly because of this here, because of the cancellation. We cannot really say that omega is equal to 0. Yeah, so far so good. Now we have omega, and the remaining part here would be to, let's get rid of this, let's say omega val is square root of 6. Now the remaining part would be to look for the absolute value. Now since we know what omega should be, we can directly plug it in. So instead of using this, we might go ahead and use the following here. So instead of this, maybe use omega val or square root of 6. And let's see what we will get as a result. Now you can see that we have minus 1 divided by 7. Now we will take the inverse of this and take the absolute. So k val should be equal to 1 divided by the absolute value of this. As you can see, k val is equal to 7. So it is possible to use frequency domain methods even though you don't have any body plot. And you can see that plugging in omega directly into the transfer function gives us the necessary data that gives us the stability bound here. So we have basically shown, seen, let's say, body methods. We have basically seen 4 different methods to obtain the same information here. Arc j omega should be minus 180 degrees, and then k should be 1 divided by abs of j omega at omega star. There we go. Now, the last part of this question is about the time delay that can be added to the system. Now, in order to analyze this part, let's first use the body method itself. So let's plot the body plot and then look for the information that would be necessary. So let's say part C. Now let's first look at the body plot. So we have the body plot here. So instead of looking for a p-type controller, we are looking for a amount of delay that would be added to the open loop plant, and then we take the unit feedback here. Now, the way of the instability that can be concluded from the body plot is always the same. So remember that we had the following. We said that, okay, the closed loop transfer function is given as k times gs and 1 plus k times gs. And since we're plugging in omega, we could also write down the following. Since our p-type controller is a static gain, it will not be affected by s equals j omega. And what we get would be something like this. So this relation given in line 38 can be also stated in line 39, which is supposedly the frequency equation, or in the frequency domain. So now the problem was the following. In order to emulate the process of going to infinity or going out of bounds, which corresponds to instability, in order to emulate that, we said that the denominator can be equal to 0, and if that happens, we have sort of an infinite gain, and at that point that would be corresponding to our definition of instability. Now, if this is equal to 0, then what we get is the following. We get k times g omega equals minus 1. If this happens, if this occurs, then we have instability. Now, the way that I've derived this, I could also apply the same method to the part where I add some delay. Now here, the closed loop is not k times gs, but gs times, let's say, d for delay. And I know that the delay would be something like this here. Let's say minus td s. So that would be the amount of delay that I can add to the plant, and then take the closed loop. So for unit feedback, I would get this one here. So at this point, I have a similar approach here, but I don't want this to be equal to 0. So the denominator here should not be equal to 0. So yeah, now we have, again, this multiplication should not be equal to 0. Now at this point, it's quite obvious that we have a duality between the p-type controller and this here. Now, if you remember previously, we concluded that if k is, for example, positive, if this is a positive gain, then, for example, the argument of k would be equal to 0, because it's a positive static value. And the absolute value of k would be, again, equal to k. So it would not change. Therefore, looking at the argument of k times g omega would equal to argument of k plus argument of g omega, which would then reduce down to argument of g omega. And the same goes for the absolute value. Absolute of k times g omega would be equal to absolute of k times absolute of g omega. And then we know that this is equal to k. We can conclude that this would be k times absolute of g omega. So therefore, if this should be equal to minus 180 degrees, we use the expression given here. So we look directly at the body plot, phase diagram, and find the frequency where this is satisfied. And then we go ahead and use this here. This should be equal to 1. We use this relation in order to come up with a p-type controller. Now, it was also possible to look for the following, where k was negative, because that's the second case that could appear. So in that case, we know that these here would be a bit different. Now, this would be 180 degrees or minus 180 degrees because of a negative value, since minus 1 is converted into 180 degrees or negative 180 degrees. This is basically the same. And we also know that the absolute value of k, since k is negative, should be minus k. So this expression here is quite easy if you think about it. We have minus 2, and all that we say is it should be the negative of minus 2, which gives us a positive 2, which is obvious, but maybe not symbolically. So therefore, we say that the argument of k is 180 minus 180 degrees, and the absolute value of k is minus k. So if we plug it in here, we can see that here we have a negative sign. Here we would have minus 180 degrees plus argument of this should be equal to 0. Therefore, for the negative stability bound, we conclude that this should be equal to 0. So we look for the point where this occurs, and then we plug it in. But when we plug it in, we have k equals minus 1 divided by the absolute value of g omega at omega star. So therefore we have directly a negative value, which should be the case because k was already negative. So therefore we used body for positive k stability bound. We used minus 180 degrees, read the omega star, and then used omega star for the absolute value here. And the same goes for the negative one. Now, in this case, we should work out what the relations should be, or what we should read from the body plot for the amount of delay that can be added to the system. So it's practically the same. We should analyze this using the absolute value here. Let's say, by the way, if you plug in s equals j omega, what happens is the following: j omega, and that's it basically. Now, absolute value of this times this. Now, if you remember, you can see that the exponential term is given here, and the absolute value of these would correspond to the multiplication of their absolute values. But the absolute value of this here, it's actually known. So since this is j omega, this would be something like j theta, let's say theta. So this is actually cosine of theta plus I times sine of theta. And we know that the absolute value of this, if you have absolute value here, we would get the following. This would be cosine squared plus sine squared of theta, and this would be equal to 1. So therefore I know that the gain here should be, or the absolute value should be equal to the absolute value of g omega. Now, if we look for the argument, something similar happens here. The argument of this, instead of looking for that, I might go ahead and use the argument of this, and we can see that the argument of the imaginary part divided by the real part, which is basically this here. And instead of using argument, I can go ahead and use a tan. Now, interestingly, we have sine over cosine, which gives us tan, the tangent, and then a tan tan would give us theta. So the part that comes with delay, the transfer function of delay, basically is very kind to us in the frequency domain. the only thing that we should remind ourselves is that its absolute value is equal to 1, so adding delay would not change the body plot in the magnitude plot, basically. And it would just have a theta effect to the phase plot. But since there's a negative sign, we can immediately see that this should be minus theta. So it will subtract theta from the phase plot, and the magnitude plot would not change. So this is interesting. Now we know that this is sort of the absolute value. Now for the argument, let's work that out. We have g omega times this e term argument, but we know that instead of multiplying them, we can add them. So the argument of this plus the argument of the exponential term would give us the following. The argument of g omega minus, and then the internal here, omega times td, basically, or td times the delay part, how many seconds it is, and then times omega. So that's it, basically. Let's get rid of this part. At this point, we know that the absolute value should be equal to 1, and then the argument should be equal to minus 180 degrees if we want to get a instability. So abs g omega is equal to 1, and the argument of g omega minus td times omega should be equal to 180 degrees. Now this is degrees, don't forget that this is degrees. But here omega is radians over seconds, so omega is basically this here. So if we want to calculate it, we might add something like, maybe we could use minus 3.14 here, but then you have to convert this one too. So maybe times the 180 degrees and then divided by pi. So this would be the conversion that is necessary here. So at this point, we can see that the p-type controller has a gain contribution, does not change the angle values. If it's a positive, okay, of course. If it's negative, it will bring negative 180 degrees to the phase. And the opposite appears or happens for the delay, where the gain is not changed in this where gain is not changed this time, but we have a negative angle contribution, which is of course not a good thing, because if the amount of delay will increase, if it's increasing, then you will get minus 180 degrees faster. So if TD increases, so if delay increases, if it's going up, something like this, we know that omega will go down in order to meet this requirement here. So if you have more and more delay, then this will happen sooner at a lower frequency. So how can we determine this by using the body plot? Now, instead of looking for the phase angle behind minus 180 degrees, what we are looking at, we are looking for the gain equals 1. If the gain passes through 1, which is 0 decibels somewhere here, we will have a frequency, and we will read the angle there, and then we see that this much margin is left for 180 degrees, which is obviously somewhere here. So this margin and the frequency where this happens will determine the amount of delay that can be added to the system. So this is how we can determine how much delay we can add, and then use a unit feedback and determine its stability interval. So by the way, this is called basically the phase margin, what we're looking at, because at that frequency we have a certain negative value, and then there's a margin to minus 180 degrees, or a distance to that, that will give us the phase margin here. So how can we calculate this? Let's see. Now we have, let me get rid of everything here. And also maybe the body plot here. So let's look for these. We should start with the gain value here. So what do we have as gain value? Yeah, we have this one here. So this would be 6, the absolute value of this would be 6 divided by the real part and the imaginary part squared and sum, and then the square root of that. So it would be a bit tricky, but it should be still possible. So let's look at this. It did not help out that much. So can we... Yeah. I guess we have... Yeah, we have to work our way out. So now this whole thing here, I guess this one here, should be equal to 36, because 6 divided by something square rooted. So pretty answer. So we can see that the square root here, and then we have this one here. Of course, this might give us a high degree polynomial, which is likely the case here. So let's expand the expression. Let's call this expression, and note that it should be equal to 36. So let's expand this expression, which gives us the following here. Now, luckily, we have omega squared, omega to the 4th, and omega 6. So before we calculate anything, what we should do is we should substitute omega squared with a new, let's say, variable called x. And then we, let's say, expression 2, substitute into expression omega squared. Into this, we should substitute this. Now this hopefully this this did not really help, but we can maybe instead of doing this, we could just say factor it out. Maybe omega squared factored out. We can I guess we should use factor on its own. Yeah, we can now see that we have basically omega times omega times omega squared plus 36 times omega squared plus 1, which basically resembles the root locus distance condition, if you think about it. Now, this should be equal to 36, so this is basically the same. So omega squared, let's write down omega squared times omega squared plus 36 times omega squared plus 1. Of course, using pen and paper and trying to solve this is quite difficult, and the design of this question is not really meant for it. Maybe if you have a simpler system or a special case, if this is a final exam, then either the equation that is necessary here, for example line 44, will be given to you, so you can directly use that, or the equation that comes out here will be much nicer. So therefore, don't worry about high level equations like this. You don't really have to solve this. So let's see what MATLAB finds us here as a solution, even if it's finding one. So let's try to solve this. Omega equals 0. Interesting. So I guess MATLAB even didn't calculate this one here. Oh, because maybe 36 here, of course. So yeah, it kind of found something, but let's see what it is. Yeah, it found 0.7814. Now, as I've mentioned before, this would be there would be two cases. One being that this will be given to you directly as it is, or there would be a better or simpler equation that you can solve. Now, we found that omega should be equal to this here. Let's double check if this really works. Let's say omega val equals this, and then omega val equals omega val being positive. So you can directly use 1 or 2 as an index in order to eliminate the unnecessary parts. But I use this to automatically get the frequency that is positive. So what we should do is we should first substitute this back into g omega and see if it's really equal to 1. And it seems like we have a bit of a problem here, because it's not equal to, or it is equal to 1 maybe, but we need to look for the absolute value. That's the case. And there we go. The absolute value is indeed equal to 1, but this value is also important because instead of taking the absolute value of this, as you've seen, there was a complex number. That complex number can give me the phase angle that I'm going to look for. So you don't really have to go back and use the argument here and then a-tan and then all the trigonometric stuff. You can just, since you've calculated omega, evaluated omega, you can just evaluate the transfer function at that omega. That will give you a numerical result, and then use your calculator maybe to convert this into polar coordinates, and that's it. So looking for the angle of g val, so the imaginary part divided by the real part, then the inverse tangent basically. So omega val, and then the absolute value here. Now we can see that the absolute value is this, and then we have minus 2.3636. Now, of course, this is not really in degrees. If you multiply it with this divided into pi, you can see that it is 135 degrees, but I don't really need degrees because I use radians. So I can stick with this and then remember my equation here and work out what this multiplication should be. So this should be equal to minus pi plus the argument of minus the argument of g omega. So I should calculate this. So let's say val, the value is minus pi and then minus the angle condition here. So there we go. Now we have val. Now this is the distance, and since it has a negative there, maybe I can just switch back to negative. So negative of this. So there we go. We have 0.77 and then we have TD times omega. Now what was omega? The omega value, basically. It is almost identical. So I can see that my TD, the value of delay that I can add to the system, is the ratio between the value and my omega value where this happens. So let's see what TD in seconds is. 0.9957. So approximately 1 second of delay can be added to the system, and then the closed loop constructed with this structure should give me a marginal stable or even unstable closed loop response. So let's check it out. Let's try to validate our results. So it should be a feedback of GS times a transfer function of delay, and that's basically it. So in order to specify delay, I'm using IO delay here, and then comma, and then the value TD. So let's directly use TD. Maybe a little bit less is necessary, but let's see. you can see perfect oscillation. Now what this means is that this is at j omega. It is a sine wave oscillating between 0 and 2. So we've basically determined the amount of delay that can be added to the system using the body plot, but not the body plot itself, but the data from the body plot or the frequency domain approach here. So it might be a bit of a mouthful here, but it's really not that difficult. The only issue that you can stumble upon is the equation that comes up here, and therefore if it's an equation that can be solved, it will be provided to you in that way. If not, then there will be a helper equation for such cases, because you're not really expected to use some numerical solution stuff here, for example Newton-Raphson or stuff. You don't really need that. So in order to prevent time wasting, that would be handled the way it should be. So let's recap, and for the recap let me use my PDF because a better documentation is available there. So what we've done in this part here is we've looked at the p-type controller, stability interval, and then also some destabilizing delay that can be added to the system. So let's start with A again. We have this closed loop here, k times gs divided by 1 plus k times gs. And we've looked for the closed loop expression because at this point we can use the polynomial methods that are available to us in order to determine the stability interval. One of them being the direct substitution, s equals j omega, which results in j omega cubed plus 7j omega squared plus 6j omega plus 6k, which is basically a complex number. And you can factor it out in a way that you have a real part and a imaginary part. So at that point, if you equate it to 0, you have real part equals 0 and then imaginary part equals 0, which would give you two set of equations, and one will be helping you out in determining what omega should be, and the other one would give you the corresponding k value, square root 6 and 7. Now, we also looked at the frequency approach here and how we can obtain the same information using the frequency method. And similarly, we've plugged in s equals j omega, but instead of viewing the characteristic polynomial, we looked at the transfer function as a whole. And this is also a function of omega, and this is basically a complex valued function of omega. And what we've done is we have looked at the absolute value, which was basically this: rearrange the denominator into real and imaginary parts, take the squares and sum them and take the square root of that. Gives us this one. The phase angle of this transfer function would be then the following: 6 divided by minus 7 omega squared plus j 6 omega minus omega cubed. Now at this point we know that the argument function here has some properties, some useful ones. Argument 6 is 0, and then this is in the denominator, so minus argument of the denominator, and since this is a complex number we can use a tan, and then we have this here. So a tan equals 0 gives us this should be equal to 0, and then we get omega 0 and omega squared root of 6. Now here's also the investigation of the point of instability, and you can see that basically this point here is, if we have a unit feedback, if k is equal to 1, then the system itself should be minus 1 in order to get instability. So from there we can see 0 decibels or the gain 1 is what we look for, and then negative 180 degrees is what we need here. Now you can look at the body plot and conclude that 2.45 is the place where 0 decibel crossing happens. Therefore, if you plug it in back into your transfer function, you get a polar representation, and the gain is 0.14 and the angle is 180 degrees. So keep in mind that a transfer function in the frequency domain will always be a function, a complex valued function that you can always evaluate if you know omega. The only issue here would be to determine omega and how to determine omega. That's the toughest part here. Once you've done that, you can plug it in, revalidate your result, look if you have satisfied that what you were looking for, and use that basically. And you can see that the inverse gives us the k value here, And then there's a body plot here. And we can see that we were looking for minus 180 degrees at the same frequency. We looked at the body graph and we read that k should be equal to 7. And when you use a higher value than 7, you can see instability happens. If it's just about the stability, you can see that there's a high oscillation, very, very low damping ratio, still stable, but at j omega, somewhere around j omega. Now, in order to determine the amount of delay that can be added to the system transfer function, we have added e to the power of j theta, and then examined this one. So the absolute value is equal to 1, so we got rid of that, and then we have this expression, which gives us basically these results here. So the argument should be equal to 1. The body plot for delayed systems or the systems without the delay will be the same, but the phase will be shifted with the delay times omega. And since omega is, by the way, the x-axis of the body plot, once omega becomes too big, then the phase angle will be approaching practically minus infinity. So, looking at the same point here, we've seen that there should be some theta value that we're after, and we looked at the gain equals 1, which we've determined in MATLAB, and then we have used the same, the omega value, we plugged it in, and we got that 135 degrees was the angle. So the distance between this and 180 degrees is theta, so minus 44.5 approximately, and then tau times omega gives us basically the amount of delay that we can add to the system. So if we use this as gs and then take g divided by 1 plus g, we get the following result. Now, this basically concludes this part of this question. So keep in mind that there will be more of these. So there's question 2, and that will be another video.